So we created the SR latch and thereby invented RAM. But it has the problem of invalid states. That is, if you give it the set and reset signal at the same time, it goofs up. And furthermore, you can have accidental invalid states and wrong sets and all this other stuff in complex transistor logic, which is why we added the clock signal. So we solved that problem. However, it still has the invalid state, and if you give it that invalid state, it still goofs up. Now, if you can prevent that using your clock signal, that's fine. You're safe. But it's nice to make sure that we can't goof it up no matter what. And furthermore, there being an invalid state seems a little wasteful, doesn't it? We've got 2 wires, which means we can give it a total of 4 signals, but only 3 are useful? So why don't we actually do something with that other state, with that other input rather? So instead of being an invalid state, it serves a purpose. Let's make a JK flip-flop. The JK flip-flop is just an SR flip-flop with a small upgrade. The reason for the different name is it's named after the person who invented it. J roughly corresponds to set, and K roughly corresponds to reset. So the letters are in the same order. So the SR flip-flop is just our 4 NAND gates. We have our clock signal that goes into both. We have our set signal into that one, reset signal into that one. So that comes out into this one and this one. The output here is Q. The output here is not Q. This takes not Q as an input. This takes Q as an input. And there's our SR flip-flop. So just like before, let's think about the problem. If set and reset are both 0, we're fine. If set is 1 or if reset is 1, we're fine. The only time we have a problem is when set and reset are both 1. That goofs up everything. Let's just assume enable is on, the clock is on, because if it's off, nothing happens anyway, so enable is on. The point of the set signal is to turn Q to 1, and the point of the reset signal is to turn Q to 0. So set is Q1 and not Q0, reset is Q0 and not Q1. So what we're telling this thing when we give it both the reset and set signal is, I want you to set and reset. But it's already going to be set or reset. So let's say it's set. Let's say Q is 1. We tell it set and reset. So we're telling it to do the thing it's already done, and then we're telling it to do the other thing. So why don't we just tell it to ignore that? If we give it both set and reset, one of those is going to be useless, and one of them is going to do something. Let's just make it ignore the thing that doesn't do something. So when Q is 1, when it's set, giving the set signal doesn't serve a purpose. So is there a way we could make it ignore that? Well, when Q is 1, Q naught is 0. So what if we make this a 3-input NAND gate? What if I take Q naught and give it as an input? So in order for the set signal to be sent, the enable has to be on, set has to be on obviously, but also Q naught has to be on, which means it has to be in the reset mode. In order for set to go through, it has to be not set. Similarly, we can put Q here. In order for the reset signal to be accepted, to be passed through to the latch part, control and latch, we cannot be in the reset mode. If Q is 0, that means we are already reset, so reset does nothing. So this right here is the JK flip-flop. This is J and this is K. You just use different letters. It's the same thing. It's the same signal. You just have the outputs feed back into the inputs and you call it JK so it's less confusing. The same way we say flip-flop versus latch. But it is an SR flip-flop with that extra pair of connections. And that's it. That's the upgrade. And furthermore, think about what actually happened. When we give it both signals, it ignores the one that does nothing and uses the one that does something. So it prevents the invalid state of giving the latch itself both signals, but it's always going to be the one that does something. If we're set, and we say both set and reset, it's going to reset. If it's reset and we give both set and reset, it's going to set. It toggles. We have now made a thing that toggles. Every time you give it both signals, it flips. Whatever it is, it flips. This is a super cool thing for doing things like counters and other stuff. Anything you want to go back and forth, there you go. Technically, it could be a square wave generator. You'd have to give it a square wave to get a square wave, though. There's one problem that you may have noticed, however. What if we give it the set and reset signal? Let's say it's set, we give it set and reset. So now it's reset. But what if we're still giving it the set and reset signal? What if we just turned those on and left them on? Well, if it's set, it'll reset, and then it'll set and reset and set and reset and set back and forth as fast as it possibly can. Hey, cool. We just made an oscillator. That's not what we're trying to do, though. So that's a problem. Another problem is, what if there's a very small delay? What if these two gates don't operate at exactly the same rate? You know, physical differences, they're two physical different transistors. Well, 4 different transistors. Let's say, for just a handful of nanoseconds, just very briefly, while this is switching, both Q and not Q are both 1. Just for a handful of nanoseconds before it settles, and everything goes great. So now, you've got set and reset over here, you've got Q and not Q both 1, and now you start pumping a 1 to both, and you're in your invalid state, and everything's going back and forth, and it's super goofy. There's 2 ways to solve this problem. One way is to use something called edge triggering to create not just a clock signal, but a clock pulse. A normal clock is on, off, on, off, on, off. It's a square wave. But a pulse would be like on, off, on, off, on, off, where it's just a super, super short high followed by a very long low. And I'll show you different ways to do this, one of them a delay gate, in future videos. But if we assume enable is just a pulse, just bam, bam, and then it's low for almost the entire thing, what happens is the clock pulse is 1 for long enough that these 2 gates will conduct, right? Let's say we have J is set and Q naught is set, and then E is set for a brief period. So this will conduct, it'll put out its low, and that'll start affecting this gate, and the feedback will start happening. But by the time that that is propagating through, this one is already turned off. It doesn't need to be on for long because the feedback will sustain it. The signal has to be on only long enough to get the feedback changing. Remember, each of these symbols is an independently powered set of transistors. So once you have gotten one of these feedback transistors to send out the feedback signal that's going to get the other transistor to do its thing, then you don't need to do the inputs anymore. It's sustaining itself until the next time you override the feedback. So you turn on your clock just long enough to kick the feedback into changing, but that doesn't change Q yet. It just changes it causes the transistors to begin to move, and then you stop it again. And by the time Q and not Q have actually changed, enable is off. It's been sitting there off for a while. So yeah, Q and not Q will be goofy, but the problem is solved. So you can use edge triggering to do this. And the symbol for this with edge triggering would be, you'd have your J and your K, your Q and your not Q, and then you might have E, or you might have clock or something, whatever symbol. But if you add edge triggering, you get a little triangle, like that. That means when the clock will normally be low. When the clock goes high, it'll go high very briefly and then go back down. That's called rising edge triggering. When the clock goes up, it'll very quickly go back down and it'll sit down. So there's 4 different edge triggerings. You can have a clock that's usually low and it pulses high when the base clock goes high. It can pulse high when the base clock goes low, or it can pulse low when the clock goes high, pulse low when the clock goes low. It basically modifies the base clock signal, because the base clock signal is going to be, your crystal or whatever, and it's going to go high, low, high, low, high, low. And then you edge trigger to create a pulse from that clock signal. So you can create a low pulse or a high pulse, and you can have it be on whichever edge. We'll get into that later. But that's one way to solve it. The other way to solve it is add more transistors. There's something called a JK master-slave flip-flop. Basically, we just add another layer to this, and it has this internal interlocking active on each half of the clock signal. It's really cool. But if we just perform the thought experiment, just to understand this, if we pretend that this is edge triggered and it's always fine, then we at least understand it. And all we had to do is add Q and not Q to this. And the enable, just like before, so this would be still the same 8 transistors, and then you can optimize by having 1 transistor for enable that's shared by the 2. So this is still 7 transistors. It's the same thing as an SR flip-flop. And so so each of these is 3 inputs, so that's 3 transistors each. These are 2 inputs, so that's 2 transistors. So it's 3, 6, 7, 8, 9, 10. 10 transistors. And then you can do just like before and have your enable signal shared, have a single transistor. At the bottom, it has to be, if you're using the serial arrangement, like NPNs, you would have your final NPN be the enable one, because obviously it has to be shared, and after that you can't split it again once you join the signal adjoined. So you can actually do it with 9 transistors. You basically just add a transistor for Q and Q naught to the existing gates, and that's all you do. So we'll discuss further upgrades to this bit of memory in the future. Until then, I'll be seeing you.